for what we have concerning homogeneous equations with real or complex roots. And just let's say that we're looking at real roots, and then we'll go into complex roots, and then we might look into a blend of both. But let's say if you're looking at solving for y, okay, and we'll say that we have something like y double prime plus 5y prime, and we'll say that we have minus 3y is equal to 0. Okay, and if we take what we have here and put in terms of a characteristic root equation, okay, so we have r squared plus 5r minus 3 is equal to 0. And we have with this trinomial, okay, we have an expression that cannot be factored, and we can determine the roots by the use of the quadratic formula. Okay, so you have like negative b will be the negative of 5, and we have plus or minus the square root, and we have b squared is going to be 5 squared, and we have minus 4ac, so we have minus 4 times 1 times negative 3 and we have all over 2a, which is going to be 2 times 1. And what's going to happen, okay, if you notice we have 5 squared minus 4 times 1 times negative 3, so we have negative 4 times 1 is negative 4 times negative 3 is a positive 12. 5 squared is 25, so we're looking at, in this case, we have 25 plus 12, which will be 37. So you're going to have a couple of irrational roots. Okay, so we can say that we have at the one end, we have negative 5 plus the square root of 37 all over 2, and we have negative 5 minus the square root of 37 also over 2. And these would be the two distinct real roots. And in terms of how to express the solution for y, well, guess what? Even though both of these terms are irrational roots, they're still real roots. And yes, we're going to end up taking y of x equal to c sub 1 times e, and we have like times all of, let's say, negative 5 plus the square root of 37 all over 2. So you have c sub 1 e times this whole expression raised to, yep, you have e to this whole expression multiplied by x, and we have plus c sub 2 times e. And that would be your general solution for what we have in terms of y itself. So you can have some crazy roots, okay, and the solution we have for y might look like a rather strange set, but this is what we would have in exact terms. Now, for what we have in the case of complex roots, and now I'm going to give you something that's going to be referred to as the Euler formula or the Euler equation. And this is going to be tying in complex numbers. You may have seen this before, or you might not have. But let's say that if you have e raised to the ix, and that is going to be equal to the cosine of x plus I times the sine of x. And some of you, if you've seen this before, or if you have not, you might be wondering, well, how can you prove something like that? Well, we are going to look at that in another part, and that's going to be concerning Maclaurin series. Okay, and you have seen more than likely some forms of Taylor series, Maclaurin series, and those series also include complex roots and dealing with the powers of I. Okay, but you have the Euler equation, e to the ix is equal to the cosine of x plus I sine of x, and that can be proven on the basis of what we have with series operations. And let's say that if you have, perhaps the most basic homogeneous equation that's going to have complex roots, and let's say if we have y double prime plus y is equal to 0. And if we translate this into a characteristic root equation, well, we're going to have r squared plus 1 is equal to 0. And if I isolate r squared, well, we're going to have the r squared is equal to negative 1. And guess what? We're going to have the r is equal to plus or minus I. So we have upon first glance, okay, you're going to have y of x is equal to c sub 1, and say we have times e to the ix. And we have plus c sub 2 times e raised to the negative ix. Okay. And if you notice, we have e to the ix, we have cosine of x plus I times the sine of x. And now, and I'm also interested in e to the negative ix. And let me give you just a little bit of a background. Okay, now just going back to trigonometry for just a moment. And we have, okay, like dealing with odd functions, even functions. And just to kind of provide a bit of a rough sketch here. You see, I have like pi over 2, pi, three halves pi. See, we have at the other end of the spectrum case, we have negative pi over 2, negative pi, negative 3 halves of pi. Now let's say that if we have working with the sine wave, first of all. Okay, so you have like the sine of 0 is going to be 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 halves pi is going to be negative 1, and once you get to like 2 pi, okay, we're back to ground 0. And if you notice, you have a bit of a sine wave. Negative pi over 2 leads to the value of negative 1, negative pi, back to 0, negative 3 halves. Okay, we have positive 1. And if you notice, you can have like with the sine pattern, okay, just going back. Okay, so if you notice, you have like the sine pi over 2 is equal to 1. But if you notice that negative pi over 2, we had the sine of negative pi over 2 is equal to negative 1. And anytime you have additive inverse angles, you're going to have additive inverse outputs. So you're going to have, in essence, like the sine of negative x is equal to the opposite sine of the sine of x. And for what we have in terms of the cosine function, Okay, now we're going to have in terms of this wave pattern. Okay, so cosine of 0 is 1, pi over 2 cosine is going to be 0, and also at negative pi over 2, negative pi and pi, cosine is negative 1, and so on. And guess what? Now, a sine function is going to be an odd function where you have symmetry with respect to the origin. So both halves reflect about the origin. Whereas in the case of the cosine wave, that is an even function where you have both halves are having symmetry with respect to the y-axis. If you notice, we're going to have the cosine of negative x is going to have the same sign, in fact, same value as the cosine of x. Okay, so going back to what we have with e to the ix and e to the negative ix, again, we have e to the ix is equal to the cosine of x plus I sine of x. Now for e to the negative ix, and the ways you could look at this is that we can say we have e to the I times negative x. And that's going to be the cosine of negative x plus I times the sine of negative x. And guess what? We have with cosine of negative x, that's going to be the same as the cosine of x. And for sine of negative x, that is going to be the negative of the sine of x. So we have, in terms of the follow-through, while e to the ix goes to cosine of x plus I sine of x, we have e to the negative ix. That is going to be the cosine of x, and what's going to be minus I sine of x. So going back to what we have for the solution set that we have for y of x from y double prime plus y is equal to 0. Okay, so I want to write this without the complex coefficients. So if you notice, we have for c sub 1 we have e to the ix, so I'm going to be looking at cosine of x plus I sine of x. And then we have c sub 2 times e to the negative ix. So we have c sub 2. And for e to the negative ix, again, I have the cosine of x minus I times the sine of x. Okay. So we have in the setup. Now, if I were to look at distributing, so you have y of x. Okay, and if you notice, if I were to distribute, okay, so you have c sub 1 cosine of x plus c sub 1 I times the sine of x, and we have plus c sub 2 cosine of x minus c sub 2 I times the sine of x. And if I collect the cosine terms together, we have y of x. Okay, so we have is equal to c sub 1 plus c sub 2 cosine of x and then we have sort of clustering together. Okay, now we have C sub 1 minus C sub 2 I times the sine of x. And guess what? A constant plus a constant is going to be a constant. So we can say this sum is going to be alpha. And for the difference of what will be complex constants, that will still be a constant. So we'll just call this beta. And for what we have in terms of the solution in trigonometric terms, we can say that we have y of x is equal to a, or alpha, times the cosine of x. And then we have plus beta times the sine of x. And that would be the results in this particular case. Now let's say that if I'm blending together real and complex solutions, and we'll say that we have, let's say we have a fourth order derivative of y with respect to x, and we'll say we have minus 81 times y is equal to 0. And if I take what I have here and put in terms of the characteristic root equation, so for r to the fourth minus 81, okay, you can say we have r squared minus 9 times the quantity of r squared plus 9 is equal to 0. And the difference of squares I can factor. So we're going to have 4 roots in this case, right? So we have from r minus 3. Okay, you see we have the first root will be positive 3, and the second root, okay, we'll have at negative 3. And for what we have in the case of r of 3 and r of negative 3, okay, we have additive inverse complex roots. Okay, and for what we're going to have in terms of the solution, okay, so we're going to have for y of x, okay, working with the real roots, you see we have c sub 1 times e to the 3x, and we have plus c sub 2 times e to the negative 3x, and for 3i and negative 3i. Let me give you just a little bit, I don't want to get carried away with shortcuts, but let me just mention something. For what we have in the case of, okay, the complex roots, okay, now whatever the coefficient of the complex coefficients will be, or I should say the absolute value of the coefficients of the complex terms in the letter I, those will be the coefficients of what you'll have for the angles regarding cosine and sine. Okay, so you have like 3i, negative 3i, and these will, if you're to run through the Euler equation, okay, 3i and negative 3i, like e to the 3i, e to the negative 3i, you would have, you know, like if I had like r squared plus 9 is equal to 0, I would have like alpha cosine of 3x plus beta sine of 3x, and that will make up the rest of what we have here. So you have a, or alpha, times the cosine of 3x, and we have plus beta times the sine of 3x. And that is going to be what we have for the general solution. Okay, so again, and so just yeah, so we just sort of backtrack. Okay, so you have these items, and whenever I present stuff like this, I still get asked, okay, how did you come up with with this still. Okay, if we'll just take what we have with these formulas. And if I just project x on out to 3x, okay. So if you notice, you have your roots. You have 3i, negative 3i. Okay, so you have like e to the 3ix, e to the negative 3ix. I can just rewrite this. Okay, so you can say we have e to the I times 3x. Okay, so you notice with the Euler equation, so I'm projecting x on out to 3x. And guess what? So I have the cosine of 3x plus I times the sine of 3x. And if I have like e to the negative 3ix, well, I would have e to the I times negative 3x. So you have the cosine of negative 3x. And remember, you have an even function with cosine. So that's going to be the same as the cosine of 3x. Whereas with the sine of negative 3x, again, sine is an odd function, and additive inverse angles, okay, will lead to additive inverse outputs. So we have the negative of the sine of 3x. So we have this will come out to the cosine of 3x minus I times the sine of 3x.